basically if you look into the concept of virtual memory, the main reason why we are moving for virtual memory is to improve degree of multi-programming, so that I can able to place as many processes as possible, so that user can have an illusion that he is executing many things in a less memory area, right? Fine. So this is one of the main advantage, but at the back end we are facing many kind of problems, right? Like the things might be, if I say there will be a memory space, something like it might be a main memory. Initially all are going to be full. After certain point of time, a process is free, a particular part of the memory is free. Then in this memory, which process I have to load? That was the question for the operating system, right? Or if P1, P2 are the two processes are competing, which one I have to load first? That might be the question, right? Based on this, in this virtual memory concept, we are going to look into two major concepts. One will be frame allocation strategies, another one will be page replacement strategies, right? So frame allocation strategies means, if I am going to have multiple process P1, P2, P3, for the process P1, how many frames I have to allocate? For the process P2, how many frames I have to allocate? For the process P3, how many frames I have to allocate? That will be defined by the frame allocation strategies. And page replacement algorithms or strategies, we can say that when all are full with some process like P1, which process I have to replace when a new request will come? That will be defined by the page replacement strategies. I mean, see, if process P1 having 10 pages, process P2 having some 30 pages, process P3 having 60 pages, and I am having main memory frames are total 10, right? Let us say 0, 1, 2, 3, 4, 5, 6, 7, let me say 8 and 9, total 10 are there, right? Now the question is, for P1 how many I will allocate, for P2 how many I will allocate, for P3 how many I will allocate? That's the question. For that, they come across with many strategies. Among those, one kind of strategy is equal allocation. Irrespective of whether you require very less pages or maximum number of pages, it doesn't bother. Always I am going to allocate equal number of pages for it. I mean, for process P1, I will allocate 3 pages. For process P2, I will allocate 3 pages. For process P3 also, I will allocate 3 pages. Right? That is what we can call it as equal allocation. Right? So if you go with some other kind of strategies, right? But is it the correct way? Right? There are certain processes which requires only 1 page, but trying to allocate 3 pages, is there any advantage for it? No need. That's the reason they come up with another kind of thing. We can call it as weighted allocation or proportional allocation. Weighted or proportional allocation. I mean, based on the need or based on the how much quantity I require, and that it is going to be allocated. Right? Based on the need I require, based on the availability of the frames, I can allocate accordingly. Right? So what they will do, if this particular process P1 wants to have 10 pages free space, then if they want to distribute them equally, Can I distribute like 1:3:6 ratio? Yes or no? Because already I am having 10 free spaces, right? As per their already sizes, I can allocate in the form of distribution 1:3:6. That is what you can call as weighted proportion, weighted or proportional distribution. I can say that if I say that process P1, total 10 pages are required, and total how many requests? 100 requests. 10 plus 30 plus 60 into 10. Total how many available? 10. So which I can say it as 1. So 1 page I will allocate. For process P2, 30 by 100 into 10, 3. Process P3, 60 by 100 into 10, you are going to get 6, right? Based on the my process size, I can allocate it accordingly, so that it might be the better meaningful, right? And the third kind of frame allocation strategy is dynamic way, right? It doesn't having any in-depth about explanation. We are going to allocate the processes to the frames based on the priority of the process. It will be done dynamically, right? Fine. So just go ahead with these three kind of strategies. One is equal allocation, another one will be weighted allocation, another one will be dynamic allocation. Right? Next thing will be page replacement algorithms. Right? So these page replacement algorithms will define something like when my main memory is full, at certain point of time some part of the memory is free. In this particular area, or if the free area which I have to place, or the case is when a particular process is already available, if a higher priority process comes into the picture, which process I have to replace. That is what we call as a page replacement algorithm. Which page I have to replace in order to accommodate the new process, right? So basically various kind of algorithms are there. 3 algorithms are there. One will be FIFO algorithm, first in first out algorithm. So basically what this algorithm will say na, we are going to replace the page which have come earlier, which has arrived earlier, that I have to replace. That's it. Have you understood? When there is no enough free space and a new process comes into the picture, you have to replace the older process, or I can call it as first process, right? For example, if I say the pages like this 47 6 1 7 6 1 2 7 2, these are the pages that are requesting for us, and initially I am following demand paging approach. What is the demanding paging approach? I haven't loaded anything. Based on the need, I will load the pages. Okay, and this is a main memory, and all are frames, and frame sizes, main memory size is 3. Memory size is 3. Now, when a particular process 4 looks here, is there any process 4 is there? Page 4 is there? No. There will be page fault, right? So can I say this is a page fault or not? Because 4 is not available in the main memory, then I can call it as page fault. So I will load into the main memory. Next, I will get the 7. Again it is a page fault, so I will load because I have a free space. Next 6, page fault, I will load directly because it is available. I mean there is free space. Next I got 1, page number 1, right? Is it page fault or not? Yes, it is page fault. And is there any free space here? No. When there is no free space, what I have to do? I have to replace with someone, right? So what is the strategy that we are following? First in first out, right? Which means the oldest process I have to replace. Oldest one, right? What is the oldest one among 4, 7, 6? 4. So this will replace with 1. Next 7, which is there, hit. Next 6, which is there, right? Next one 1, which is there. Next one 2, right? 2 is page fault or not? When it is page fault, what I have to replace? 7 or 1? 7, right? If I say that 1, that is the referenced one, so you have to replace with the oldest one which have recently modified, I mean earlier modified, right? That is 7, so I have to replace with this one as 2. Next 7, which I have to replace? 6, 7. Next 2 already there, right? So total how many phase faults happen? You can count here simply 4, 7, 6, 1, 2, 7. Total 6 page faults done. Okay now, right? So for practice, try to go ahead with the of size frame 4. Right? Try to do 4 page fault, 7, 6, 1. 7, 6, 1 already there. 2. Replace. 7 is there. 2 is there. So total page faults how many? 5. Initially 4, and this 4 is replaced with 1, that is 5. You can just count them so that you can get the clear idea. Okay now. So this is the algorithm, we can call it as FIFO page replacement algorithm in point 1. Next kind of algorithm, LRU, least recently used. What is the meaning of least recently used? The one which has not used recently. The one which has not used recently, I can call it as least recently used, right? So for example, if I say the same example, 4, 7, 6, 1, 7, 6, 1, 2, 7, 2. So if I say total number of frames are 3. Frames are 3. So first 4 page fault, 7 page fault, 6 page fault. Next 1. 1 I have to replace with which one? 4, right? Least recently used, right? So I can replace with this one. Next you got 7, which is already there. Next 6 hit. Next you got 1 hit. Next 2. 2 should be replaced with what? Which one? 6. Right? Earlier one and this one is different. Earlier one we have to replace with the memory space. Now you have to replace with the least used one. Right? What is the least used one? Least referenced one. 7. Try to observe. Or else just go ahead with which page you want to replace. Now I am trying to check with the 2. Right? Least recent ఏం యూజ్ చేసామమ్మా? 1 యూజ్ చేసాము, 6 యూజ్ చేసాము. యూజ్ చేయండి ఏంటి? 7. So you can just simply replace with the 7. Right? So if you want, you can write the definition. Replace the page which has not been referred for a long time. Now is it understood? Which has not been referred for a long time, right? So how can you identify which has not been referred for a long time? You can just place wherever you want to replace the page and go back so that you can get the clear idea. So 1, 6 are already referred, so 1 and 6 should not be replaced. The one which has not been referred for a long time is 7, so that you can replace. Now go ahead with the 7. So just place here, 2 and 1 are already referred, so you have to replace with the 6. Next 2 referred. So total how many page faults? 6 page faults are there. Okay, just count them. Next go ahead with try to solve with the frame 4 frames. 4, 7, 6, 1, good. Next 7, 6, 1 is already there. 2, right? Now tell me, 2 it has to replace with which one? Right? Least recent game which is 7, 6, 1 is, so you have to replace with this one only. Next 7, 2 already there. So total page faults are 5. This is the algorithm we call it as least recently used, which has not been referred for long time. Next kind of algorithm which we call it as optimal algorithm, optimal page replacement algorithm. So what this optimal page replacement algorithm will say is, replace the page which will not be referred for longest time. Then what is the difference between the earlier one and this one? Here it is thinking about optimal page replacement algorithm will think about the future, whereas LRU will think about the earlier one. Okay, now that's the difference. So just try to solve them. 4 7 6 1 7 6 1 2 7 2, right? So if I try to solve it with the total number of frames are 3, 4 7 6 anyhow page fault. Next 1, right? 1 is not there, so page fault, right? Now this 1 has to replace with which one? Which will not be referred for long time, right? So you have to go towards the forward side, right? So 7 you are going to use it anyhow, 6 you are going to use it, and in the near future 4 might not be used. That's the thing, you have to replace with 1. Next 7 used, 6 used, 1 used, and 2. Now think about this one. 2, from this point you have to go further. You can go ahead with either 1 or 6, right? You can go ahead with either 1 or 6. So I will just go with this. That's it. So total number of page faults are how many, ma? 5. Try to solve it with the 4 frames. 4 7 6 1. So we completed all these 4, all are page faults. Hit 2. Replace with the 1 which will not be referred in future, right? So you can go ahead with either 4 or 6 or 1, whatever it might be. So I will replace with 4. So total number of page faults are how many? 5. Right? Initial 4 and later 1, that is total 5. These are the 3 kind of algorithms which I can say them as page replacement algorithms, which are very important in every great question. Every year you will get one. Okay, fine. So try to solve one set questions. If you got the pages as 0 1 2 3 0 1 4 0 1 2 3 4, right? So try to solve with FIFO, LRU and optimal for the sizes frame numbers 3 as well as 4. Try to solve them. If I go ahead with first in first out algorithm with size 3, tell me 0 1 2, 0 1 2 and then 3, right? 3 it has to be replaced with someone, that is FIFO. If it is FIFO, I have to replace with 0. 3 0 1 replace with 1 and you got 1 should be replaced with this one. Next 4 has to replace with 3 0 1 and then 2 replace with 0, 3 replace with 1, 4 is already there. So total how many page faults for us? 9. So you have just blindly count all the things. Total page faults are 9. Now the same thing, go ahead with 4 page frames. 0 1 2 3 1 2 3. Now 0 is already there, 1 is already there, 4 has to replace with which one? 0 has to replace with 1 has to replace with 2 has to replace with 3, and this 3 has to replace with this one, 4 has to replace with 0. So total how many page faults? Page faults 10. Okay now, fine. Next one, LRU. LRU, right? What this LRU is saying? 0 1 2, which has not been referred earlier for the long time. Earlier, optimal, future, right? So 0 1 2 done. Next 3 has to replace with which one? Just go back from here. 2 1 already recent referred, so go ahead with 0 and replace with this one. Next 0 1, this one 0 and 3, that should be replaced with this one. Next 4 3, next 0 is already there, 1 already there, 2 4, am I right? 2, if you go back, 1 and 0 are recently referred, so replace with 4. 3, 1 and 2 recently referred, so I have to replace with this one. 4, 2 and 3 recently referred, so I have to go with this one. So total how many page faults? Again 9. Okay now? Where 10? Okay. Okay, good. 3 3 is 9 plus 1. Next, go ahead with 4 frames. When you go with 4 frames, 0, 1, 2, 3. So next remaining these things are there. 0 is there, 1 is there, 4. If 4 is there, which one I had to replace? 1 0 3. So I had to replace with 2. Next 0, 1, 2. 2 I had to replace with which one? 3. Right? So 1 is there, 0 is there, 4 is there. So least recently used earlier is 3. So I had to replace with 3. Next 3, 4. Next 4. Anyhow, how many page faults are there? 4, 8. 8 page faults are there. Okay. What about the optimal? I have to check about the future. When I am going to the future, 0 1 2, 0 1 2. So I have to look into, I had replaced with 3, right? So 0 1 is recently referring in future. So I had replaced with which one? 0 1. So 0 1 0 1 2. I had replaced with that 2. So here this one will be 3. Next 0 is there, 1 is there. Next 4. 4 if I want to replace, which one I had to replace? Again 3 only. Okay na? Next 0 1 is there, 2 not there, so I had to replace with someone. Right? Which one I can replace? Either 0 or 1. So this one will be 2. Next 3. That's it. 4 is there. So how many page faults are there? 7. Total, just count them all. Right? Next, go ahead with 4. Right? When I go with 4, 0, 1, 2 and 3. Right? So 0 is there, 1 is there, 4. 4 I had to replace with which one? 3. Right? Next 0, 1, 2 is there, 3 I had replaced with any one of 0, 1, 2, so I had replaced with this one, that's it. So total how many page faults? 6, right? So like this you can able to solve any kind of question number, okay na? But if you are going to look into these kind of things, in generality, when you are going to increase the frames, when you are going to increase the number of frames, the number of page faults in general should be decreased. Right? If you look into LRU algorithm, here 3 page frames, so 10 page faults. When I increase 1 frame, page faults are decreased. Similarly, optimal also, initially page faults are 7, later when I increase the 1 frame, page faults are decreased. But there are certain situations where FIFO algorithm is going to behave abnormally, right? Which means even when I increase the number of frames, the page faults are also going to be increased. The counter example for that is this example only. This kind of thing we call it as Bilady's anomaly. So just a kind of scientist name, Bilady's anomaly, who has find out that one, right? So what is the meaning of Bilady's anomaly? When the number of frames are increased, what about the page faults? Increased. This is the definition for Bilady's anomaly. Okay na? In other words, I can say Bilady's anomaly not following stack property. Some situations they might give this kind of thing. Bilady's anomaly not following the stack property. What is the meaning of stack property? In such a way that when number of frames or let us say 3, I mean page fault of number of frames of 3 is subset of page faults of 4 frames. What will happen here in this particular situation? I mean page faults of lesser number of frames is subset of page faults of higher number of frames, which is a kind of Bilady's anomaly or not following Bilady's anomaly. Right? So try to think. This is what? Number of frames are 3. Page faults of number of frames, lesser number of frames is subset of page faults of higher number of frames. I mean, if I say this is K and this is L, K should be less than L. K should be less than L. When it is going to have this kind of condition, this is what we call it as stack property. Stack property, right? Try to take the counter example of LRU. LRU, how many page faults are there if the number of frames are 3? 10. Is 10 is subset of 8? 8 sir. No more. Page faults of number of frames are 4. Is 8. 10 is subset of 8? No. Which means what? It is following the stack property. So in point 1, LRU comma optimal, these two algorithms always follows the stack property. The only algorithm which doesn't follow the stack property is Bilady's anomaly, or I can say it as a FIFO algorithm. Okay na? Just note on that. LRU Not less than subset. One is part of other, right? Which means number of frames right? Just note down this in reverse manner. Superset term or greater than, right? So always lesser frames having the more page faults and higher frames having the lesser page faults. If this situation is going to be happen, that is a true one. That is a true case. We call it as stack property. Okay, now. So if you want, you in general we can go ahead with some kind of diagram representation, but it is not required for you. Just change this one. Okay, next one. You can go ahead with another kind of algorithm, working set algorithm. Working set algorithm, right? So if you look into either FIFO algorithm or LRU algorithm or optimal algorithm, what is the main concern here? The page faults rate is depending upon number of frames which you have taken initial, right? So that some users will take very less number of frames, some users will take more number of frames depending on the situation, right? But this is not the accurate criteria. So that is the reason we are moving for working set algorithm. Okay, now. So I will try to explain this with an example. Let's say there will be pages 1 to 3, 1 to 4, 142, 151, 24, 21. These are the pages that are available for us for the request in order to place in the main memory, right? So generally this working set algorithm works based on, so I can write the definition. Nearest feature is a close approximation of recent past. Nearest feature is a close approximation of recent past, means which is going to combine both LRU as well as optimal. LRU as well as optimal. And here we are going to consider one more parameter. That parameter is something like window size. Window size. So based on the window size we will decide. Let's say our window size is 4 more. Our window size is 4, which means that what? Maximum I can able to accommodate only 4 processes. 4 processes. If you want, I can reduce them If you want, I can able to increase maximum of 4 processes. But earlier, always it has to have 4 processes. Right. So initially, my window contains only one process. Next, I can have 2 processes, 1 and 2. Next, I can have 3 processes, 1, 2, 3. Listen, you can write. Next, I got this one. Right? So which means that initially I have taken this one. Next, I have taken 1, 2. Next, I have taken 1, 2, 3. Next, what is the window size here? 3 only. No problem. Can I include one more? 1, 2, 3, 1. Yes, no problem. Even I include 1, 2, 3, 1, my window size will be only 3. Right? Next, I will move my window size to further. Right? Up to here it is done. 4. Next. So what will be the window? 1, 2, 3 only, because 2 is repeated. Next, I will move my window towards further. Next, what is this window size now? 1, 2, 3, 4. Next, I will move 1, 2, 4. Next, 1, 2, 4. Next, next also again 1, 2, 4 only. Next, 1, 2, 4. Next further 1, 2, 4, 5. Further 1, 2, 5. Further also 1, 2, 5. Anywhere did the mistake? Where ma? Okay, let me continue with my explanation. So 1, 2. Ma? Okay, so check here. I have taken up to here 4, 1, 4, 2. Right? What is the process here? 1, 2, 4. Right? Next, I will move towards right side. So then I can go ahead with these 4. When I go ahead with these 4, again you will get 1, 2, 4 only. Next, these 4. This 4. When I move, you will get 1, 2, 4, 5. Earlier, same only, right? Window. Next, I will move the window, which is 1, 2, 5. Window I will move, which is again 1, 2, 5. Ma? 4 already done, right? 4 already done its task, and I am moving the window size towards next step. That's why I have removed 1, 2, 5. Next window, which is 5, 1, 2, 4. So 5, 1, 2, 4. Next 1, 2, 4. Next 1, 2, 4. So do I need to move further again? No need, because it is done. The last element, last page has completed, so I no need to move further again. That's it. Fine. So this is the working set algorithm, how it works. Right? So here you might get the question, how many frames referred on average? Right? For that, what you can do now, you can try to count all the things. 1 plus, 2 plus, 3 plus, 3, 4, 3, 3. I have written the count of all the things, and these things you can note down. 3 plus 3, 4, 3, 3, 4, 3 and 3 by total number of pages. How many total number of pages are there? Or 15? 16. You can note down. This is the average number of frames referred. Okay. So this is the way a working set algorithm will work. That's it. It's a simple one only. So which will combine both LRU as well as optimum. Anyhow, I will share the PPT. You can note on that. Next one, segmentation. Right? In the earlier concepts of paging, what we are doing? We are going to divide a process into n number of pages of equal partitions, equal sizes, right? So when you are going to do that, sometimes the related parts of the program might fall into different partition. So then it doesn't having any meaning. For example, if I say there will be a function which I have written some set of lines of code, right? And if this part is falling into this area and this part is falling into this area, is there any meaning for it? It doesn't having exact meaning, right? That is the reason we come into the concept of segmentation. Means instead of dividing a process into multiple parts blindly based on the size, we are going to divide the process into segments. What are these segments? Segments means simply they are having some meaningful. They are having certain kind of meaning. I mean, if you look into the main memory, so some main segment will be is one partition, and F segment is one partition, data segment will be one partition, stack segment will be one partition. Like that, every partition having some meaning. But earlier cases we are not going to follow like that. So this concept we call it as segmentation. Now how here the conversion is going to be happen? In general, CPU is going to generate a logical address, which you might know that. So in the paging concept, what is happening here? Page number is going to be given, large number, right? Here you will get segment number, not the page number. And here what is there? Offset will be there. And instead of page table, here we are having segment table. In the segment table, we are going to maintain two columns. One column will be related to base address of a segment. Another column is related to limit of the segment, up to which location it has to access, right? So basically, once I got the offset I am going to compare with the limit. If the condition is satisfied, whatever the offset that they have generated, if it is less than the limit, then it is going to be added the respective base, and that will be referred to the main memory. So this entire concept we call it as segmentation, which is very, very simple. So just go ahead with this particular structure. Okay. So basically offset is there. So in general, this has done in the paging concept, right? At that time you are going to get many confusions how we are going to do all the things. But if you go with the segmentation, these are all going to be resided only one location, so there won't be any kind of problems. Okay na? So this entire concept we call it as segmentation. That's it. So at the end here, what will be there? The respective data. Okay, you can stop here. We'll continue the next class.